Hi everyone, thank you for coming. This is my research development of a coupled CFD and FEA model for whole building fire performance determination. And this is a talk on why it matters. I'm Daniel Fellows. I have several supervisors, Dr. Sean Walton, Dr. Jennifer Thompson, and Professor Ube Hassan from Swansea University. And I have two industrial supervisors, Kevin Tinkham and Ella Quigley from Tata Steel. So just want to go over a couple of key terminology first. One is CFD, which stands for Computational Fluid Dynamics. And essentially we use that to model fluids and air. And then we have FEA, which is finite element analysis, and that is used for structural analysis. And then what we mean by coupled is basically getting two softwares to communicate with one another. There's two types of coupling. There's one way, which is where we have software A, which does all the solves the entire solution. And then once that's done, it then exports the results to software B, where then software B takes that data into consideration and runs through the solution. Then we have a two-way coupled, which is what we're trying to attempt, where we have software A does a part of the solution, then sends that data to software B. Software B takes that data and does part of the solution, and then feeds back that data to software A to then carry on, and the cycle repeats. So why is this important? On the 14th of June 2017, the Grenfell Tower caught fire, resulting in 72 deaths. And just last year, we had the Torre del Moro apartment block fire in Milan. Why Tata Steel are interested in this is to do with primarily the cladding material around the buildings. So in the Grenfell Tower, an appliance caught fire on the fourth floor, and the whole building was then ignited as the cladding material caught fire. And with the Torre del Moro apartment block, the fire was actually started through an appliance again, but on one of the top floors of the building. And it is said that the fire, as soon as it ignited the cladding, it took an unnatural path down the building. So it is an extremely hazardous material as it stands right now. And recommendations from the Grenfell disaster suggested a move towards safer building materials. However, fire testing on new products can be costly and negatively impact the environment. Henceforth, we have a need for a numerical model to be made, which accurately predicts thermal and structural analysis for full-scale buildings to reduce the amount of experimental testing done to develop new products. So this is to say that we're not trying to replace them at all, as we still want the experimental tests to have the final say on a product and have the final approval. But we want to not have to burn 100 products and scale that down to maybe just having to burn 10. So who's involved? As I was mentioned before, previously, Tata Steel are involved. They proposed this project, and they came to Swansea University because Swansea University is Tata Steel's partner universities. It's already hosted a number of projects within the university and is at the forefront of innovative buildings. The project will also utilise the modelling expertise associated with the university, including my supervisors. And a little about Tata Steel, if anyone doesn't know, they are a global steel producer that operates within the automotive, construction and engineering industries. And within construction, where this project is focused, they manufacture sandwich panels for various parts of the building, including cladding and roof panels. The goal is to modify a numerical model that will be able to simultaneously carry out CFD and structural analysis calculations on a whole building fire with Tata Steel products. And for this software to then be used as a reliable performance testing method for new cladding and structural materials, which can then be scaled up to whole building tests to locate hotspots and problematic areas, and then also looking at sub-assemblies to get a detailed analysis of how those products react within a system. So we're currently up to, where we're up to right now is that we've discovered an open source CFD solver called Fire Dynamic Simulator. And we have taken that software and completed one benchmark case already with it, where we were modeling a pool fire within a industrial standard room called ISO room 975. And we found a paper with a large amount of published results, and it required minimal components to model. This paper focused on simulating the fire within underventilated conditions by narrowing the doorway. And we were able to draw several conclusions from the study, one of which is that comparative results were made. As you can see from the graph, as we refined the mesh, we were able to gradually get results closer and closer to the experimental data. And another one was an aspect that's been noted within the modeling under ventilated conditions, where the turbulence within the room is actually rotates in an anti-clockwise manner. And that was, we also were able to model that and predict it, as well as the fire's behavior, where within the unventilated conditions, it reaches out the doorway and burns predominantly there as it reaches for that oxygen source. The plan for the future of this project is to complete a second benchmark case, which is more applicable to Tata Steel, which is we're going with a sub-assembly of a cladding structure. Haven't managed to get accurate results yet due to the fire, but for the benefit of this presentation, I've just put in a standard fire to show the animation clip. And once we get the comparative results from this with a previous experimental case, we are then looking to develop a one-way coupling system. So we're taking the thermal data and that from the FDS, and then we're going to find a structural analysis software and export the thermal data into that. And then, having completed this benchmark case, we then look to then go on to develop the two-way coupling system, which is our goal for the entire project. Thank you for your time. And that is the end of my talk.